modulation of multiple signals, right? So I can always go back to DFT. I can also go back to Fourier transform and so on. So in this work, in this part of the small talk that I'm going to do, I'm going to talk about some classical approaches and some recent approach which we have created. And the idea here is to create to understand how can I detect the images which are compressed in JPEG and can it be generalized. Well, we all know that whenever there is a camera that takes a picture, it creates the image on the sensor, and that is a very rich information content. And from there, we compress it to go to a JPEG image, right? So this is like any camera, irrespective of whether it's smartphone or your DSLR or any other device. In many cases, just detecting this JPEG compression itself becomes a challenge. And I'll motivate how and when to do those things. But very common use case scenarios is this copy move forgery detection, right? So for those of you who have followed the media recently, there has been these images of war that is coming up, right? And suddenly you see that a particular city has been bombed while the image has been taken a couple of years ago, right? So the war images from 2014 has been recirculated again with some new images by putting some new content inside that. So which is typically a case of cut paste, right? And the journalists, when they get these kind of images, they really have to find out whether this image is taken yesterday, like a week ago from the war, or it has been taken like 10 years ago. So there comes the idea of this age estimation of the image. And then I also gave the example of this PR and new based approaches, which is very relevant when you know the source of the image, where it's originating from. And in many other cases, for instance, in this pornographic video, most of you have seen that there have been celebrities that have been misused for creating their images, right? So for adult content. And then you would be interested in finding out if it's actually this person or if it has been repurposed for malicious intent. Good. So if you go back to the history of this work, there are a plethora of works that you can look at. I only take a couple of images which are directly relevant in our case. One way of detecting this image is going into the frequency domain. Now, how do we go to the frequency domain? Because we all know that in the JPEG, we have this encoding, which is typically this block-based encoding, right? So as long as I understand that encoding, so what I could do is like I could reverse it and then get the histogram of each particular block, the DCT components. And again, now remember this work was done in 2012, pre deep learning era. And then once you have this, we always have this likelihood estimation. Use the theory of likelihood estimation. Given this image, given this DCT coefficient, what is the likelihood that this is a manipulated image? And then just by simply looking at the local maxima detection, they figured out, okay, I not only can say that whether this image has been manipulated or not, but I could also say that if it has been compressed or not, but I can also say that which areas are there exactly compressed, right? So how do you do it? How do you go for an image compression? You try to remove the redundant information. If the information is repeated continuously, you just encode it as 1 followed by 8 blocks, right? So now, if you can identify these areas, then you can also show that areas where exactly this has been manipulated or compressed, right? Gives a rough idea. Understandable? Yeah. Okay. And then following those ones, after the deep learning era, then came the other approach, which again is based on looking at the quantized DCT coefficients, which is QDCT on the top area, and then from that they subselect some of the DCT components. And once they are subselecting the DCT components, what you could also do is you could say that, well, in addition to that, I also look at the image information. So what is essentially happening here? So they're combining the spatial information with the frequency information. The top part is the spatial information here. Sorry, the bottom part is the spatial information here, and the top part is the frequency information. So once you have them, you combine them. Now you don't have to learn an end-to-end network to learn everything. So you are making use of custom features to learn two fully connected networks, two fully connected layers, here and here, this and this, and then you have a class label which says whether it's compressed or not compressed. Good. And then we have the The other motivation, so this is one of the recent works that we published in IWBF, and here the goal is, if you look at the top image, you see that the face image is almost not changing, right? So maybe if you zoom into some areas, which I'll do in a short while, you can see that there is some effect, but it's hardly noticeable. So what happens in this case is that there is a standard which says for passport issuance, you cannot provide the images which are not more than 2-level compressed. So the 2 level of compression comes from two factors. One is the compression at the camera level, and the second one is at the issuing level, where it's compressed as JPEG. And then comes the third level, which is at the authority level. So whenever the passport office in India wants to store it in the database, what they do is they do one more level of compression and they store it. So what this means is that by the time you give your photo to the passport office, it should not be compressed more than twice. So the motivation is to detect if it has been compressed more than twice, right? And the problem again, if you look at these images very carefully, so this is single compression, which means after the camera, it has been converted to JPEG. Then I go to the next compression, which is at the quality factor 90. In JPEG, you have different quality factors, right? So you have 90, 80, 30, and so on. So you can compress it at different level. So if you see this image, I hardly notice any differences, right? And then if I compress even further, 80, it's still unnoticeable. But maybe somewhere in quality factor 10, you start noticing some subtle changes. If I zoom it here, now you see this small subtle artifacts, the block artifacts that is coming up, right? So the question then comes down to, irrespective of the person has gone from this area to any of these images, we should be able to detect them. What is the motivation? The motivation is now clear. Now what can we do about this one? So Professor Nithanen gave a very nice talk about this gradient distance, right? That means that any network that you're using, they will have some gradients. So if the image is not compressed, or if it's compressed at one level, the gradients will be very different from the images that you're seeing, which are multiple level compressed. For instance, look at the same image here, which is at 90, and then here at the activation maps, which is nothing but the gradient maps, right? So your gradient maps overlaid onto the image, you see the activations are very similar, some changes, and then if you continuously do it for all the different compression levels, suddenly you see that at this quality factor of 10, you have very high activations. You see the changes across all of these. So from this one, 80 to 90, sorry, 90 to 80, it is more activated. 90 to 50, it's even more activated. As we progress, you are having very high activation. So this kind of gives you an indication that the gradients can tell us something about the image level, image quality, image compression, right? So if I have that one, how can I design a network so that is somehow agnostic towards different systems? So in this case, it was a joint work that was done with NIT Calicut, and then the student that just recently graduated, he came up with the idea. So if I have an image, the reference image, I don't know what quality it is, whether it's double compressed, triple compressed or not. I only know that this is my image that I have to make a decision on. Then on that, you can again initiate second level of compression. So by doing so, you're going to get new set of activation maps, right? So to get the activation maps, again, I could use any of these networks that is available. But since we know that FRS models the face recognition models are dedicatedly trained to look at the identity features, the features that are very relevant to face, I can extract the embeddings from them. Now we are not going to the latent space, rather we are directly attacking the gradient space. So in the gradient space, I see the differences here. And then I also assume the image that I have, which I don't have any idea about, I do the same process here. I pass it through FRS model, I get the class activation map. Now, as soon as I have the class activation map, then it's if the image is of 2 megapixel, I have to deal with all these 2 megapixels. So instead of doing that, what I can do is like I can say that I have a rough coarse segmentation map, which is nothing but some areas are divided into different blocks, right? So if I zoom this one into this, so in this case we were segmenting it to 50 different regions. All of them are do have some kind of semantic meaning, right? And then from here we formulate it as a simple problem. If the image is unmodified, the region should remain consistent across all the different compression levels. If that is not the case, that means that it is going to tell me that how many ranks are flipped and how many ranks have remained consistent. So just to take a simple example here, if I'm taking from so if I have the image here, and then let's say 4 regions, and then for the compression 1, C1, C2, C3. Now for each of them, the same regions. So in this case, if this has been ranked number 1, and in this case it has rank number 3, and again rank number 5, 4, sorry, 1, 1, 2, 3, 4, 5, 5, yeah, 5. And then here it's flipping from 2, 1, 4. That means that the rank list has changed, right? So now I'm not doing any kind of deep learning here. So I'm using the gradients. I'm using the region segmentation on the gradient, and now I'm seeing the rank list. For this, the rank list is for the region 1, it's 1. For the region 3, maybe 2, and so on. And now in this case, the region 1 has got rank 3, the region 3 has got rank number 1, and so on. Now this is nothing but a simple correlation factor, right? So if it is not compressed, all the ranks should remain consistent. If I can measure the proportion of ranks that are flipped, so that can indicate me that it has been compressed or not compressed. So the idea here is that we go back to using any of the existing networks, look at the gradients, and then group them into different segments, and then measure how many ranks remain consistent, how many of them actually flip. So by doing this, you can establish this flipped rank matrix, and then we have the classifiers, and that classifier can be any classifier, any of your favorite classifier, including your MLP based classifier. And then you can say the labels, which is compressed, double compressed, or not double compressed. Okay, and then what exactly happens in this case? So how did we come to this motivation, right? So if you look at the factors, all the activation that we have in a particular network, you see that they are quite varying. So if it is singly compressed, the more you compress, the trend goes upwards, right? So it's nothing but a box plot. It's a violin plot which shows that how many of the points are lying in each region, and they kind of tend to increase in this case. And if it is quality factor 90, now you can see that for the quality factor 90, it has slightly differed, right? So now compare this one with this one. So it is changing, and the characteristics change again when it is 80. Now there is a change in this part and this part. And look at the 30. So the 30 factor, which was here, which had the rho value, which is the correlation coefficient, which was around 0.1 mean. Now it has shot up to 0.6. Gives an idea? So this means if you have such an observation, you can always make use of the gradients, and then you can try to design a classifier. Okay, so then how do we benchmark this? If you look at benchmarking this, there is this very popular network which is called as MantraNet. It's a work done by colleagues in US, and they came up with this very generic architecture which could detect fakes versus real images using a simple CNN based architecture. And in this case, we took, okay, this is the closest state of the art that we can compare against. And when we compared our architecture against this, you can see across different quality factors, it's kind of improving the results. It's consistently improving the results as given to the MantraNet. Now again, in the defense of MantraNet, we should also be aware of the fact that it was not designed for this purpose, but it's still usable in this case, right? So the comparison is not one-to-one, but still it's somehow comparable. Okay, good. And then we also wanted to see, okay, this method looks very nice and fine for JPEG compression. Good. But then JPEG compression is not the most popular compression, right? So JPEG is used in the passport issuance, fine. But on the media, on the internet, there are also a lot of other compression aspects. For instance, WebP is a very popular format. So we wanted to check how it works there. And the same tendency you see here. So you go from 85 to 96 here. Okay. The lower the compression, the better, the easier it is, or lower the compression factor, the easier it is to detect. Right. So if I have a very low quality which is corresponding to QF10, then it's much easier to detect. Okay, and then also to see that how much it can vary across different generalization schemes, such as if I train the system on one kind of images, JPEG images, and if I want to test it on different kind of images, how does it scale? Does it scale or does it fail? So in which case we see that MantraNet is also doing quite well, or MantraNet is doing quite well, which is around 80%. And in our case, we see that it goes to around 85%. So this is a very recently opened up area, so it might be of interest for some of you who are looking into this forensic angle. So you could potentially extend it for all different kind of compression schemes, and inherently you can also extend it for video-based systems, where you can see instead of looking at one frame compression, you can try to see if one particular frame within the video has been compressed or not by looking at the temporal coherence. Good. I think that was remaining from yesterday, so which I did not manage to cover in the synthetic content creation detection. So now we have a complete picture of detecting the content from GAN-based approaches, diffusion-based approaches, to something that is more trivial, which is using the standard compression schemes like JPEG or other schemes which are mainly designed um, to to save the space. Okay. So then you have a picture of that. So with that, I don't know if I should continue with the next lecture, or are we breaking for lunch and reconvening again after? We can break for lunch and then we'll start. Yeah. Okay, so then we will start talking about morphing attack detection, and then we'll progress towards presentation attack detection, and then we'll talk a bit about aging in FRS using synthetic approaches. Yeah, yeah, please, please. Oh, sorry, I did not take any questions. You were saying that this compression can be used for the video part, yeah? Yeah. So, do you mean to say, this I didn't got the crux of it, do you mean to say that we are dividing them into individual frames? Individual frames, yes. So, on each frame, we can apply this gradient descent and see how much gradient descent shift is there, like what we are seeing in this particular, in that particular two video, and maybe manipulated video. Exactly. So if I look at the video itself, I can think of two situations, right? Situation number one, the whole video has been manipulated, or situation number two, the whole video remains as it is except few frames, right? So in which case, what I should do is that so I say that I have a frame number one, frame number two, frame number three, and so on, right? So in which I assume that only this frame has been manipulated. So now what I can do is I can look at this gradient maps of this one, something like this, and the same for next one, and the same for next one, same for next one. Now, hypothetically speaking, if you have if the compression level here is let's say x, this one is, let's say, make it as y, y1, y as well, y as well. Only this frame, which has been inserted into that, has a different compression. So let's say it has a compression z. So the rank correlation between y, y, and y for the similar content will be very similar compared to what is z. Right? So in which case you can say, okay, this particular frame has been manipulated. Now when it's the whole video, then it becomes a bit more complicated problem. So then you have to look at every frame, and the reason here is that you can measure the correlation between these as well, right? Not just the reference and frame number one, but you can also measure reference and frame number one, frame number one to frame number two, frame number two to three, difference between this and any of the other frames, which is in our case this one, will be different. Gradient maps. Other questions? Okay, then we break for lunch and then we meet again at 2 o'clock.